So this video is on electrophilic addition. So electrophilic addition occurs with alkenes, and it's where the double bond opens up and substances are added onto the carbons in the double bond. So the overall equation for a general electrophilic addition looks like this. You start off with an alkene, in this case ethene. You add a substance with two atoms bonded together, so this is X and Y, and you can see that X joins onto one carbon and Y joins onto the other carbon. So let's look at the mechanism for this. So here we have our alkene. So our alkene has a double bond. A double bond consists of 4 electrons in between these two carbons. So each bond, covalent bond, consists of 2 electrons, so we've got a double bond here. So this is an area of electron density. Electrons have a negative charge, so it's an area of negative charge. Okay, and electrophiles are attracted to areas of negative charge. So an electrophile, electro meaning electron, phile meaning to like, so attracted to areas of electron density. It's addition because if you notice the overall equation, nothing's being removed. So there's nothing being eliminated, nothing being substituted. You're just adding stuff on. So X and Y are going to get added on. X and Y in this example, they're going to have they're going to be polar. So X is going to be partially positive and Y is going to be partially negative. So that means that Y is the more electronegative element and X is the less electronegative element. Now, this mechanism does actually occur with molecules which are not polar. So things like a bromine molecule, Br might attach onto that. And that's because as it gets closer to this area of electron density, the electrons are pushed away. So the electrons here repel any electrons here, push them away. So we always end up with this partially positive area here and a partially negative area here, even if it wasn't a permanently polar molecule to begin with. So how do we show the double bond opening up and forming a bond with X? Well, you use curly arrows. So again, you show, and if you can't remember what curly arrows, please watch the video before on nucleophilic substitution first. So I explain curly arrows there. So a curly arrow comes from the center of the double bond and goes towards the partially positive X molecule. So that's forming a covalent bond between one of the carbons and this partially positive X atom. Now, this X atom is, in this example, can only have one bond. So, like a group 7 element, can only have one bond. So, something's got to break, and a bond that breaks is this bond here. We show that with another curly arrow coming from the center of the bond, going towards this atom here. So this atom here is going to gain its electron plus X's electron, so it's going to form a negative ion. This ethane molecule has donated 2 electrons onto the X. So it's essentially given away one of its electrons to X. So actually this is going to form a positive charge. Let's have a look at that. So we can see that the curly arrow here has formed a covalent bond between this carbon and X. Now, in this situation, the X could have actually attached onto this one as well. It wouldn't have made any difference. So both things would occur, but actually it wouldn't make any difference to the final product. So we've ended up, because the double bond broke, and has now joined onto the X, it's essentially donated one of its electrons to the X. So this whole molecular ion is one electron short, is one electron down. That's why it's got a positive charge. And if you look at how this bond broke, both the electrons went to Y. So both the electrons went to Y, so therefore Y gains its electron plus X's electron, so therefore has a negative charge. So what we show now is this is like an intermediate, this doesn't last for very long. These two get together, this lone pair here, we draw a curly arrow coming from this lone pair going towards the positive carbon. And by the way, this isn't partially positive or partially negative, it's a fully positive and fully negative. So the Y comes along and forms a dative covalent bond with the fully positive carbon. I forgot to mention the way we say this bond is splitting here. We say this bond is splitting heterolytically. So heterolytically is when there's an uneven split. So both the electrons go to one of the atoms. It's the opposite of homolytic fission, which you may have learned about in free radical substitution, where one electron goes one way, the other goes the other. And now we can see that from here, we go down to here, so the overall product you form is X is joined to one of the carbons and Y is joined to another carbon. So let's now look at a real example of this. So this is an electrophilic addition reaction with ethene and hydrogen bromide. So you can see that they are added on, nothing is removed, nothing is substituted, they are added on, the hydrogen and bromine, forming bromoethane. Bromoethane. So you wouldn't write it like I've written it here, I've just done that so you can see that the hydrogen's been added. Actually, you'd write it like this. So you can see that there's 3 hydrogen there, so it's CH3, CH2Br, hydrogen bromide. So the electrophilic addition mechanism starts off like this. You have your ethene, you have your electrophile here with the one with the partial. So the hydrogen is less electronegative than the bromine, so the hydrogen gains a partially positive charge. The bromine is more electronegative, so partially negative charge. So the hydrogen starts closer to the double bond, and we show a curly arrow coming from the center of the double bond going towards the partially positive hydrogen. Hydrogen can only have one bond, so this bond breaks, so both electrons go towards the bromine. So we can see what is formed. You can see the hydrogen is added onto one of the carbons. Again, because this is symmetrical, it doesn't actually matter which one it adds onto. We'll talk more about that later when it does matter, but at the moment it doesn't matter. So we're added onto this left-hand one. Okay, you've got both the electrons from this bond have gone to the bromine, so the bromine has this pair of electrons here, a negative charge. Because this double bond has it's formed a dative covalent bond with the hydrogen, it's essentially given one of its electrons to hydrogens, hence this thing's got a positive charge located on this carbon, and we show a curly arrow coming from the center of the lone pair of the electrons going towards this positive charge, forming another dative covalent bond with this carbon, giving us this final product that looks like this. So you can see the bromines added on here. So we've now got bromoethane. So in this example, we've got ethene again, and this time we're adding bromine, a bromine molecule, Br2, so 2 bromines, and you can see electrophilic addition, we end up with dibromoethane forming here. So what's the mechanism? Well, it's very similar to before. So you draw your ethene even, you draw your bromine molecule. You might be thinking, hang on a minute, why have I given bromine a partially positive and a partially negative charge? You'll be thinking, these are the same atom, they've got the same electronegativity. This is not a polar bond. And you'd be right, but what happens is as the bromine molecule gets closer to this double bond, this area of electron density, these electrons push or repel the electrons in the bromine closest to it. So the electrons in this bromine, which is closest to this double bond, are repelled downwards, so repelled towards this bromine. Because there are now more electrons around this bromine, it gains a partially negative charge, whereas this one's got a partially positive charge because it's slightly electron deficient. We then show a curly arrow coming from the double bond towards the partially positive bromine. Bromine can only be bonded to one thing, so we show a curly arrow, this bond here breaking, and both electrons going to this bromine atom, forming a bromine ion. The rest of the mechanism is then exactly the same as before. So one of the bromine adds onto the carbon, and then this forms a positive ion, this is a negative ion. We show a curly arrow coming from the lone pair on this one, adding on here, and you can see that overall we've got dibromoethane formed there. So overall you can see what's happened. There is the initial stage, where the bond opens up, you form this intermediate, as the other bromine adds on, bromide I should say, forming dibromoethane. If we look back at this example we did previously with the HBr, we're going to look at this exact same mechanism, but we're now going to look at it with a unsymmetrical double bond. What do I mean by that? Let's draw that. This this molecule here, this is but2ene, and you can see it's symmetrical, the same as ethene was symmetrical. This molecule down here though, prop1ene, is not symmetrical. So when you have a non-symmetrical alkene, you get a small complication, which we're going to talk about now. So when we add HBr across prop1ene, we can get this option here occurring where the bromine sits on this carbon here on the end. So this would form 1 bromopropane, or the bromine can add on to the middle carbon, forming 2 bromopropane. Sorry, I'll say it again. 2 bromopropane. So 1 bromopropane, 2 bromopropane. So we end up with 2 products. Okay, and one of them we get more of. So one of them we call the major product, and one of them we call the minor product. So we're going to go into look at how these form and why one of them is formed more than the other. So in this example, we've got prop1ene, okay, and the first step, there's no difference. So the double bond opens up, attacks the hydrogen, this bond breaks, bromine leaves. Okay, so the hydrogen is now added onto one of these carbons. Now, this is where the complication occurs. So which hydrogen does it add on? Because if the hydrogen adds on to this one, it means the bromine will add on to this one, so you'll end up with 2 bromo. Or if the hydrogen adds on to this one, the bromine will add on to this one, so you'll end up with 1 bromo. There's 2 possibilities I'm going to draw. So here's possibility 1. Okay, so you can see the hydrogen's added onto this central carbon, so the bromine's going to have to add on here, so we're going to end up with 1 bromo. And here is possibility 2. So this time the hydrogen is added onto the carbon on the right. So you're going to end up, the bromine is going to attach to the central carbon, so we'll end up with 2 bromopropane. So in reality, both will occur, but this one in the bottom will occur more. So this is what's known as the major intermediate, and will make the major product 2 bromopropane. So to understand this, there's 2 ways to look at it. There's the simplified way, and this is the simplified way. The simplified way is this. The hydrogen, to form the major product, the hydrogen always adds onto the carbon that already contains more hydrogen. So the hydrogen for the major product adds onto this carbon because it's got 2 hydrogens compared to this carbon, it's only got 1. But the real reason behind this is a bit more complex, and it's to do with the formation of this intermediate. So these intermediates are these positively charged organic compounds. They're called carbocations. Carbocations. They don't live very long. They're intermediates because they have this positive charge. They react very quickly. But some of them are more stable than others. This one is a more stable carbocation than this one. So this one, the one which forms the major product, is a more stable carbocation. And it's more stable for this reason. So this positive charge is located on this carbon here. This carbon is attached to this group here. This is the general term for this is an alkyl group. This is specifically a methyl group. The general term is alkyl group, so carbons and hydrogens. Now, alkyl groups are what's known as electron releasing. So this alkyl group gives some of its electrons to the positive carbon. And this alkyl group also gives some of its electrons to the positive carbon, effectively spreading the positive charge out around the whole molecular ion, causing this molecular ion to be more stable. If we look at this positive carbon here in the minor intermediate, which this one will form the minor product, this carbocation is only attached to 1 alkyl group. You see it's only attached to 1 carbon, whereas this one's attached to 2 carbons. Because it's only attached to 1 alkyl group, it's only got 1 alkyl group donating some electrons to it. So therefore this positive charge is not going to be very spread out. Because it's not very spread out, it's much more unstable. So that's why it leads to the minor product. So let's continue on with what happens with these mechanisms. So for the minor intermediate, the bromine, the double bond on the bromide ion is attracted to the positive carbon and forms a covalent bond there. With the major product, the bromide ion at this time attacks this positive carbon, the one in the center. So we can see with the minor product we end up with 1 bromopropane, and the major product we end up with 2 bromopropane. So if we look at this whole mechanism, we can see there is the whole mechanism going the 2 separate ways. So we've got the minor and the major. So the major product is the one that happens most. Both happen, but the major one happens most, and the minor one happens the least, due to the stability of the carbocation intermediate formed. Now this is what's known as a secondary carbocation, because it's got 2 alkyl groups. This is the primary carbocation, because it's got 1 alkyl group. And you might imagine a situation where there might be a tertiary carbocation. So a tertiary carbocation could look like this, where there are 3 alkyl groups on the positive carbon. So this would be even more stable. So this would be forming an even major product. I mean, for this to form, you'd have to have some sort of branched chain alkene.